Hello, everyone. Okay, guys, can you hear me? Okay, very good. So let me get my slides. Okay. Okay, so I'm glad to see that you are enjoying Flex Week so far. So because it's Flex Week, I am not allowed to teach you anything new, right? So I was thinking what I could do with you, and I decided to update the practice problems. So I added a bunch of practice problems, but I didn't have time to replace the ones that are already on the web, but I will do it straight away after the class. So now you have, let's see how many. You have 11 problems. They kind of comprehensively cover what we did so far. And on Wednesday, we will go through, try really hard to find time before Wednesday to try to do the problems. And then on Wednesday, we will go together through them and see how to solve them. So that's the first thing that I wanted to tell you about. Next thing is I decided to give you, so it's not really new material, but it is it's a kind of applications of what we have done so far. So let's see what I have prepared for you. So another application that is really, really important for practice of maximum likelihood estimation is the following one. Assume that you have, say, 10 voltmeters, and you have to measure certain voltage. Before you measure that voltage, you went to the lab and you tested all the voltmeters, comparing their readings with the readings of a super precise, expensive lab quality voltmeter. And say you tested with 100 different voltages, all of them, and for each of them you computed its variance, right, which would be the measurement of, so the variance, how would you compute it? Well, that would be simply, of course, it's empirical variance approximation of the true variance. It would be, if you measured 100 times, it would be 1/100. And then measurement of your voltmeter V, and then sum here, right? I equals from 1 to 100. And then measurement of voltage I minus the reference voltage I, that's the super precise one that you can use to approximate the true value, and then squared. So this will give you approximately the variance of the voltmeter I. Let's call it like this. In fact, here I shouldn't be dividing by 100, but I should be dividing with 99, because this is really not, well, actually, you know what, this is a lab quality voltmeter, so it is actually the true value of the voltage. So that would be perfectly fine like this. So once you have and say some voltmeters measure accurately to 0.01%. That's voltmeter 1. Then you found out that the second voltmeter measures with accuracy 0.5%. So that would be the standard deviation, say. And then maybe you have one that is measuring with 100 times as large variance as the first one, and so forth. And maybe some of them are totally lousy. Maybe one of them measures with the error of, say, 2%, which is actually pretty good for a handheld voltmeter. So after you've done this testing of your voltmeters, you go to the place where you have to measure your voltage, and you have to decide how to do it. So if you have these voltmeters and you know exactly their errors, how would you measure the voltage? Which voltmeters should you choose to do the measurement? If you know the variance of all of them, intuitively, naively, what do you think? Which one should you use? Pick the one with the smallest variance. That's exactly what everyone would kind of have gut feelings, because if you have a very accurate one, why would you bother with the less accurate ones? But unfortunately or fortunately, this is not the case. What you should do, you should measure with all of the voltmeters, and so you would have a measurement, let's call it M1 of voltmeter 1 with variance V1. Then you measure it with voltmeter 2 with variance V2, and measure using the voltmeter 10 with variance V10. And then what you should use, you will estimate the voltage that you want to measure as sum when I equals from 1 to 10 voltmeters that you have. And then you will take a reciprocal of the variance of the voltmeter I, normalized by dividing it by a sum over all j of voltmeter reciprocal of variance J, so J also goes from 1 to 10, times the measurement of voltmeter I. So even it actually matters. Even if you have a lousy voltmeter, you don't want to throw away its measurement. And we will later see numerical experiments. The thing is, you use all of the voltmeters you have, and then you make a weighted sum. Notice the sum of the coefficients here, right, is exactly 1 because it's normalized with the sum of all reciprocals, right? So the weight VI is 1 over variance of Y divided by the sum J equals from 1 to 10, 1 over the variance J. So this aggregates all the reciprocals. And with this weight, so your Vx will be sum I equals from 1 to 10, this weight Wi times measurement I. And this is kind of counterintuitive, but actually this method provides a hugely more accurate estimation, even when there is a great discrepancy between the accuracies of the individual instruments. And you can see why this is important. For example, you instead of voltmeters, maybe you have, say, tutors marking exams. Well, if you kept track of how well they did in the past and you evaluate their variance, to get the most accurate mark, you would ask several tutors to mark, and then instead of taking the average, the simple average, you will take this weighted average in which the weight given to the ith tutor will be reciprocal of his variance. And so this fact is extremely important in machine learning, right? If you have some estimators that are of different accuracy, you can actually aggregate them and boost the accuracy of the resulting composite estimator in this way by weighing the estimations with the variance of the individual estimators. So now we want to see why this is so, right? Because it's a really an important fact. So this is what I've been telling you. Okay, so one assumption that here we make, which is in practice often true, is that these estimators are unbiased. So a tutor does not want to give you on purpose lower mark or a higher mark. If a tutor would mark a large number of your assignments, on average, the expected value should be the correct value. So we want to see what happens if, so you see, because each measurement necessarily involves noise, right? Is this central limitation theory? It's not quite central limitation theory, but all of these things are related. We will talk about CLT later. So what is the, well, there are several, well, I guess only one central, but limit theorems. One of them simply stating that the average of random variables, identical equally distributed random variables, will converge to the expectation of that variable. But there is, of course, the central one that says if you have a bunch of identically distributed independent random variables with any probability density, so with any probability distribution, their mean converges to the normal distribution. So that's the reason why in our work we often make the assumption that the noise will be Gaussian or normally distributed, right? Gaussian, because in real life, the noise comes from a large number of independent factors. You know, if you are measuring voltage, then part of the noise comes from radiation of from outer space, comes from some of them comes from electromagnetic radiation of cars around you and all sorts of machines. And so in this case, it's reasonable to assume that the noise will have Gaussian distribution, because it's a sum of a very large number of independent variables, and then central limit theorem tells us that we can assume, we can approximate it well with a normal Gaussian distribution. Okay, so now, so to kind of formally put it, we have n sensors, right? And let's call them that have readings x1 up to xn, and such that the errors of the readings are independent. Sensors are unbiased, so expected value is equal to the true value, and that they are normally distributed, but with a different known standard deviation sigma I, right? So let us now see what would a maximum likelihood maximum likelihood estimator tell us how to find the true value. And let's denote the true value of the measured quality equal to mu. So we want to determine mu, but of course we don't have direct access to mu. We only have noisy measurements x1 up to xn. So since the sensors are unbiased, the expected value of the readings of all sensors is the true value, is equal to mu. So let us see. So now what you do is you take your measurements with your voltmeters, and you have to come up with an estimation of the true value. Well, one way is to reason like this. Let me see what value of mu would make these measurements as likely as possible. Okay, so you took the measurements, you recorded your, say, 10 voltages, and now you have to come up with an estimate what is the true value. And one way of doing it would be to look for a value, for the true value of the voltage that would be the most likely to produce outcomes equal x1, x2 up to xn. You are with me? So just arguing, so to speak, reversely, you know, if you yeah, so here we don't know what the true value is. We only have noisy readings, and we want to find out what value of mu would be most likely to produce these measurements. So now, well, what is the likelihood of seeing such measurements? Because the errors, so what is the error? If x1 is the measurement, the error will be x1 minus mu, because mu is, we assume that's the true value, and it's also expectation of all of these variables because the voltmeters are all unbiased. Because they are because the noise is independent, right? The noise of each sensor is independent of the noise of the other sensor. Of course, this might not be always a very realistic assumption, because if, say, the noise comes from electromagnetic radiation, it's, well, you might assume that it's kind of random fluctuation that changes its voltage in any instant in time, and that your measurements are reasonably spaced in time, so that the noise between the noise is uncorrelated. We actually make a stronger assumption that the noise is independent, right? So because we have independent events, then the likelihood will be product of the likelihoods for each measurement. And we know for normal distribution, we have this normalizing factor 1 over the standard deviation times square root 2 pi, and then e to this minus 1/2, and then value, measured value minus true value squared, so that's the square of the value of the noise, divided by the square of standard deviation, or just the variance of the ith sensor. And now it's easy to see that you can aggregate these guys together and these guys together, and you get product of these factors and product of e's. You can put them under a single e, and of course the exponent will become a sum, right? And now, so this is our likelihood, and now we want to see for what mu is this expression as large as possible. Well, we know how to do that. We differentiate the likelihood with respect to mu. So what do we get? Mu doesn't appear here, so that's a constant, goes outside. And then the derivative of e to something, well, that's exactly e to something, times the derivative of the exponent. Well, the derivative of the exponent will be minus 1/2, and then the derivative of the square will produce a 2, right? It will produce a 2 that will cancel this 2 here. And minus here will cancel this minus outside. So what you get will be just the sum of linear factors divided by sigma I squared, right? So that comes just straight from here. Now, we have to set this equal to 0, and of course, this whole factor is never 0, it's always strictly positive. So the only way that this is 0 is if this sum is equal to 0. But you can break this apart. This is sum of xi divided by sigma I squared minus mu. I can take out mu and sum just reciprocals of sigma I squared. So this is what I get. And in solving that, I get that most likely mu is exactly what I told you with the story with the voltmeters. Namely, you weigh measurement of each sensor with the reciprocal of its variance. So let's see, I think I have a, yep, here. So reciprocal of its variance normalized with the sum of the reciprocals of all variances times xi. So important thing to remember is that, well, let's first see how good this estimate is. Well, let's compute its variance. Clearly, because it's a linear combination of unbiased variables, it will be unbiased in self. So to compute its variance, we just have to find the expectation of the estimator minus true value squared. And lo and behold, you can put both xi and mu on top here. So you will have to multiply mu with this factor, and then you can distribute it to all of individual xi's. So you get this divided by that, right? And now, if you square this, this is what you get. And now just notice expected value of products xi minus mu times xj minus mu when I is not equal to j is 0, because the noise in the two different sensors, we can assume that it is independent. So all different I and j's disappear, and only things that remain is when I is equal to j, in which case this will be squared, and this variance will be, with standard deviation, will be taken to the 4th power. And of course, we have to square the denominator. And lo and behold, from this, we can conclude, right, when they are different, they are gone, expected value is 0. So all what's left is this. But notice if I go with expectation inside, this is precisely the variance. So this will be precisely sigma I squared. And now sigma I squared cancels out 2 from sigma I to the 4th. And you get precisely sum of reciprocals, which is what you have on the bottom. And then this sum cancels 1 on the bottom, and you get just 1 over sum of the reciprocals of all the variances. Now notice, what you have is, now clearly, so this is our variance, but this sum is larger, strictly larger than any of the individual guys that you sum up, right? Because it's a sum of positive, strictly positive values. So this sum is bigger than any individual reciprocal variance. And so this can go on top and you get just the variance. So this is a proof that taking all voltmeters into account resulted in more accurate estimation, because the variance of the estimator is smaller, strictly smaller than the variance of all individual voltmeters. So it makes sense to use them all. Well, maybe this weighted sum was not an optimal way of doing it. Well, it turns out that, in fact, you cannot beat it. So when the noise is independent, Gaussian, with possibly different variances, maximum likelihood estimation, namely this weighted sum with weights equal proportional to the reciprocals of the variances, that it achieves what's the best possible. In the on the website, class website, you can look at these lecture notes that I used to teach in past years. I'm not sure if we will have time to cover it this way, but on page 6, you can find a proof of a famous theorem that says that precisely this variance, which is the variance that was produced by the maximum likelihood estimation, is the smallest possible among all estimators that are unbiased. So you cannot beat the maximum likelihood estimation. So what do I want to you to take out of this example? On the first place, when you and this happens in very many situations. For example, you want to aggregate, say, markers, the scores given by different referees, right? Or you want to aggregate customer feedback of customers that in the past have already evaluated products. If you can estimate from the past performance their variance, right, then you can in fact aggregate things in a much more accurate way than just by taking the simple mean of the estimates produced by individual either sensors or referees, just name it. So all information is valuable, even if it's of lesser quality, if you integrate it, if you aggregate it in a good way. Yeah? So this is a nice example of maximum likelihood estimation. Now, students always ask me, do I have to remember all these derivations and all this complicated stuff? And the answer is no, because the final will be open book, right, at home. What is important, though, is to understand, and look, this was just a simple algebra and basic definition of what a Gaussian is, to understand how this works, so that in the future, if you have to aggregate values from sources of different reliability, you will know how to do it. So when you read the notes at home, or the slides in this case, make sure that you understand what is happening. And if you don't, just come to my office hours and I would be more than happy to explain. Right, my office hours are on Wednesday from 2 to 3 on Zoom. And or if you are shy, drop me an email and I'll give you private consultation when you don't have to be worried what other people say or think, okay? Even though it's a very bad idea to care, to give a damn what other people say or think, because it's your life. So, so this is an important tool. How do we aggregate data that comes from the sources of unequal trustworthiness? You see, the reciprocal of the variance can be seen as a measurement of trustworthiness, but in real life, it won't be variance. This trustworthiness, you will see how many times in the past, say, a certain agent perform in an acceptable way. And you have results from different agents, right? How do you aggregate them? Well, this shows that you should take into account everyone's result, but with trusted with a different degree, namely aggregated with a different weight. So that's the first thing that I wanted to show you. Next thing that I want to show you is an application of the Markov's inequality. You remember what was Markov's inequality? This was a very simple one. If variable x is bigger or equal than 0, and it has an expectation e of x, finite, then probability that your variable will exceed or equal some value t is smaller or equal than expected value of x divided by t. Okay, so let me first ask you, so this is Markov. And you should really memorize it. You should know it because it's so important and it's so simple to remember. Now, let me ask you a question. What do you think? How large does T have to be so that this has any information whatsoever? Does this inequality have any meaning if T is small? How large does T have to be for this to make sense, to be informative? Let me help you. Can T be smaller than the expected value of x? What happens if T is smaller than the expected value of x? What is this quotient equal to if T is, so if T is smaller than e of x, then e of x over T is bigger than 1, right? Exactly. So then we would get that probability that x is bigger than t is smaller than something bigger than 1. Well, thank you very much, because we know that probability just by its definition, so this guy here is actually, we know it's smaller or equal than 1, right? And Markov inequality tells us that it's actually smaller than, say, 1.5. Well, that's completely useless because we know that probability is at most 1. So this is kind of completely vacuous if t is small. So this is designed to work when t is reasonably large. Okay, now one application of this inequality is something called Chebyshev inequality. I forget who was whose student, Chebyshev and Markov, Chebyshev actually, I mispronounced it. His name is Chebyshev. One of them, either was Markov a student of Chebyshev or Chebyshev was student of Markov, I don't remember, but I should have checked that. But Chebyshev made probably the most important application of the Markov inequality as follows. So remember, for the Markov inequality, the only thing that we assumed that x is positive or non-negative, and it has finite expectation. Chebyshev actually assumes more. So it doesn't assume that x is positive, right? But it assumes that it has not only finite expectation, but it also has a finite variance v. Then probability, not just that x is large, like in the case of Markov, but that x differ significantly from from its expected value by more than t, right, is smaller or equal than the variance divided by t squared. So instead, like in Markov, we had this t equal here and here, but here we actually have better t is increased t squared, and we and we are asking not how big x can be, but how far it can deviate, with what probability it can significantly deviate from its expected value. And the answer is that the probability that x is farther from its expected value than some number t is smaller than the variance of x divided by t squared. And it's a very simple reason why this is so. You can do it as an exercise almost. The trick is you simply notice that probability that this absolute value is bigger than t is equal precisely the probability that the square of this is bigger or equal than square of that, right? Because this happens, namely absolute value is bigger than t, just in case the square is bigger than t squared. And now just notice that this expression x minus e of x squared is a random variable which is always positive. So we can always, we can now apply the Markov inequality, right? So what do we take? So we set y equals x minus e of x squared. This is a non-negative random variable. And what is the expectation of e of y? Well, y is precisely the expression that you need to find, expectation of which is a variance, right? This is precisely the variance of the variable x. So by Markov theorem, what do we have? By Markov inequality, so notice, so we saw that this probability is identical to this probability, which is just the probability that y is larger of t squared when y is just this x minus e of x squared. By Markov inequality, this is smaller or equal than the expectation of y divided by t squared. But as we just saw, the expectation of y is just the variance of x, and voila, you get that this is smaller or equal because of this inequality, that variance of x divided by t squared. And we will need this inequality later in the course. So, okay, now let me, any questions so far? Forgive me if I'm going, I should ask you if, so please read it at home, and should you have any qualms, don't hesitate to get in touch with me. This is all elementary probability that every engineer should know. Okay, very often, you remember, for example, Karger's mean cut. We chose edges to contract with probability equal to the proportional to the weight of its edge, of that edge, right? So how do we implement this? So assume that you have k options, for example, k edges, and all these edges have weights, and you want this, the probability to pick an edge to be proportional to the weight of this edge. So probability pi, you want it to be weight of the edge EI divided by the sum when E belongs to G of all weights of E, right? So this is how you find with what probability you would pick edge EI, right? But how do you implement this? Oh, so for Markov, does the inequality inside P? It's that's a good question. Let me go back for the Markov inequality. So the question is, for the Markov inequality, do we need, yeah, I guess you can make a pathological case in which only T is, it's a constant T, so that in order to wait, so it should be non-strict inequality. Did they write it? Yeah, I guess we should put here, thank you very much. It should be bigger or equal than T everywhere. But notice, this is a singular point, right? So probability that something will be larger than certain bound T, excluding it or including it, except of course, if the variable is discrete, then of course it makes a difference. So yeah, let's keep everything. I should correct it on the slides and put everywhere non-strict inequality. Thank you very much for that. So I'll fix the slides. Very good. Simon, thank you very much, Simon. Good man. Okie dokie. So now what do we have? So how would you implement this? How would you, so you have a bunch of options to do. Say, which edge to pick. And your number generator, random number generator, usually you have functions for Gaussian random number generator or uniform 0, 1. Let's say you have uniform 0, 1 random number generator that always produces a value that is bigger or equal than 0, smaller or equal than 1. And that's all what you have. And you want to turn it into a random generator that actually outputs values between 1 and k, so that value I is its output with the probability pi. How would you do it? Any ideas? So assume that instead of this random number generator, you actually have a dartboard. And say you are uniformly equally likely to throw a dart anywhere inside here. How would you split the interval so that from where the dart falls, you can decide which P to take? And to preserve the probabilities, P1, P2, how would you split? If you chop them in k sections of equal length, the trouble is this would work if all the probabilities are equal, right? Because if you chop them in equal length, it's equally likely that you will be in any of these intervals. But you want, Donna is on the right track. Proportional to their probability. Donna, that's very good advice. So this is how we do it. First one is just so that this length is P1. The next one, will be at the point P1 plus P2, because this will make sure that this is equal to P2. The next one will be at P1 plus P2 plus P3, because this will ensure that this is equal to P3. And then you run your random number generator and you simply look what is I, so that your number is bigger than ith division point and smaller than I plus first division point. Very good. So this is how you simulate random variables with different probabilities using only a uniform generator. Okay, so now, okay, so this is, okay, so now I'll tell you what. Let's stop here, because even though what we did in this hour, we kind of used only notions that we know, like Markov inequality, or on the other hand, maximum likelihood and things like that. I did sneak in a little bit of new material, right? So that's, but I just couldn't afford time to completely kind of goof off. So let me not burden you more. And on Wednesday, we will only discuss the homework problems that I assigned you, and nothing more, so that you can in fact use this week to catch up with any kind of work that you might have. So how about we do a really short one today, namely 1 hour, and you use the next hour to read the homework problems and to attempt as many as you can, and then we will talk about them on Wednesday. Eh? Sounds good? Okie dokie. So have a good Monday and Tuesday, and I'll see you on Wednesday, and try to give it a shot at the homework problems. Okie dokie. I'll see you guys soon. Bye-bye. You're most welcome.